Hey everyone, and welcome. Today, we're going to dive into an idea that completely changes how we think about logical arguments. We're not just going to follow a proof line by line, we're going to see its actual shape. Let's talk about proof nets. Okay, so let's just jump right in. On one hand, you've got your traditional proofs. You can think of these like a recipe, right? You follow each step one after the other to get to your final dish. But proof nets? Whoa, they are a whole different ballgame. They're more like a map of the entire logical landscape, showing you how all the different pieces connect and interact all at once. So this really brings us to the core question behind this whole thing. What if logic wasn't just a list of statements? What if it was something you could actually see? Something with a real structure, a geometry all its own? To answer that, we first have to understand what we're moving away from. So let's start by looking beyond the limits of those old-school linear proofs. You know, the way most of us learn logic is through systems like natural deduction. And everything is super orderly, super sequential. Premise A leads to B, which then leads to C. It's kind of like a single train track, just moving in one direction. But that simplicity, it actually hides the deeper, more complex structure of the argument. So, if that's the old way, what's the alternative? Let's get right to the heart of it. What exactly are proof nets? At their very core, proof nets are basically graph structures. They take a proof and turn it into a diagram, giving you a geometric picture of the argument. This is a massive shift in perspective, moving us way beyond that simple line-by-line sequence we were just talking about. One source I saw calls it a parallel syntax for proof theory, and that is just the perfect description. It totally captures this idea that we're not thinking in a single-file line anymore. Instead, we're seeing logic as this network of connections, a whole web of deductions happening all at the same time. But an idea this radical, it has to come from somewhere, right? To really get what proof nets are about, we kind of need to look at their origins and the legacy of the new logic they grew out of. Yeah, proof nets didn't just appear out of thin air. They were born from this field called linear logic, which is a really cool system that treats logical assumptions kind of like resources that you can't just copy or throw away. And in this system, a proof net isn't just any old drawing. To be considered valid, it has to follow these super strict structural rules. And here is a fantastic way to understand this. Think of a proof net like a distributed computer system. For the whole thing to work, all of its parts have to communicate perfectly. So a valid proof is deadlock-free. That means there are no circular arguments, no logical traffic jams. Every single connection has to make perfect sense. Okay. So this idea came from a pretty niche field, but the real game changer is how it's now being used to power up the classical logic that underpins, well, pretty much all of modern math and computer science. And the impact is huge. We're talking about new ways to present classical logic, systems for proving when a formula is actually invalid, and even brand new algebraic structures. But maybe the most exciting part of all is the direct link they create to the world of parallel computation. So this is absolutely crucial. Proof nets offer these two incredible guarantees. The first is called strong normalization, which basically just means any process of simplifying a proof will eventually stop. You're never going to get stuck in some infinite loop. And the second is confluence, which promises that no matter how you simplify it, you will always end up at the exact same, unique, most essential version of that proof. So what does this actually look like in practice? Well, you might start with a big, complicated, messy proof full of all these redundant detours. Then, this reduction process, which we know works because of normalization and confluence, it acts like a cleanup crew. It just systematically snips away all the unnecessary steps until you're left with the absolute core, the essential argument, the proof's unique normal form. It's like all roads lead to one simple, elegant destination. So what's the ultimate payoff here? By showing us this essential structure, proof nets let us interpret logical proofs as parallel programs. The proof net itself becomes a visual of a computation, where all these different logical threads are being processed at the same time. It forges this really powerful, direct link between pure logic and computer science. So when we put all these pieces together, what's the final picture? Well, it's about way more than just a new technique. It's really about seeing logic in a completely new way. If you remember one thing from this explainer, make it this. The entire shift is from seeing a proof as a linear sequence of steps to seeing it as a single, unified geometric structure. We're moving from a line to a network. And that leaves us with a really fascinating, almost philosophical question. If a logical proof can be seen as a program, what does that reveal about the fundamental nature of truth itself? Definitely something to think about.